So we have these long, complicated expressions that we have derived for the equations of motion, but now we finally can start making some simplifications. So for part D of this question, we were setting m1 equal to m2, which we just set to equal to m, and also L1 equal to L2, which we set equal to L. And so now our two equations will reduce to 2L theta 1 double dot plus L theta 2 double dot, and we have a cosine of the difference in the angles plus an L theta 2 dot squared, sine of the difference in the angles, and that has to equal minus 2g sine theta 1. So this was for our theta 1 coordinate, and for theta 2, so that was the first equation, and then the second equation for theta 2, we have an L theta 2 double dot plus an L theta 1 double dot cosine of the difference minus an L theta 1 dot squared sine of the difference, and that equals minus g sine theta 2. So these expressions certainly look much simpler than the expressions we had before, but they're still coupled nonlinear equations that we have to solve. So that was part D, was just making those simplifications. And now we go to part E, and here the assumption was that we will make the small angle approximations. So we're going to be looking at small amplitude motions, and when we have small amplitudes, of course, sine theta goes to theta, cos theta goes to 1, and then we have these expressions that involve the cosine of the angle difference and the sine of the angle difference. And for these small amplitudes, we're going to say that theta 1 minus theta 2 is approximately equal to 0. So we're not expecting there to be large differences in the angles. And we'll see how that, we'll insert that approximation a little bit later. So first, let's make this normal small angle approximation. So our two equations become 2L theta 1 double dot plus L theta 2 double dot plus L theta 2 dot squared. And then it's a theta 1 minus theta 2. So this is I'm putting the expansion in explicitly for theta 1 minus theta 2, and also cos theta 1 minus theta 2. And that equals minus 2g theta 1, yes, theta 1. So that's the first equation. And then the second equation, we make that same set of approximations. So I have an L theta 2 double dot plus an L theta 1 double dot minus an L theta 1 dot squared. Theta 1 minus theta 2 is equal to minus g theta 2. Okay, so we have this term that still involves the difference between these angles. the angles are kept small, so we expect this difference to be small, but it's also quadratic in the velocities. And so we have a double approximation that not only do we expect these difference in angles to be approximately the same, but theta dot squared, we also expect that to be very small. And if you just think about what happens in a pendulum, if you keep the angles very small in the pendulum, the kinetic energy never gets large. So the velocities always remain small. So we have something that is quadratic in velocities and involves a difference in angles, which we expect to be very small. What that allows us to do then is to ignore these terms. So with those two approximations, we end up with our equations 2L theta 1 double dot plus L theta 2 double dot equals minus 2g theta 1. And the second equation, L theta 2 double dot plus L theta 1 double dot is minus g theta 2. So now what we've done is actually linearize our equations. They're still coupled, but at least now they're linear.